The adsorption selectivity is a commonly used metric to determine the efficacy of any microporous crystalline material such as metal organic framework or zeolite for a specified separation application. The adsorption selectivity is defined in terms of the ratio of the component molar loadings Q1 and Q2 in the adsorb phase divided by the ratio of the partial fugacities F1 and F2 of the components 1 and 2 in the bulk gas mixture. In order to answer the question, how does the adsorption selectivity depend on mixture composition, I present here data for the selectivity of carbon dioxide with respect to methane for a variety of mixture compositions in Chabazite zeolite. This is an important zeolite that is used in membrane constructs for separating methane from CO2, because both adsorption and diffusion favor CO2. I show here data obtained from Configurational-Bias Monte Carlo simulations, CBMC, for 50-50 mixtures of CO2 methane, shown by the yellow diamonds. The red circles are for 20-80 mixtures of CO2 and methane. The crosses are the CO2 methane selectivities in a ternary mixture of CO2, methane and nitrogen in the proportion 20-40-40. The pluses represent the CO2 methane selectivities in a ternary mixture of CO2, methane and hydrogen in the proportion 10-20-70. The cyan colored hexagons are the data on the CO2 methane selectivities in a quaternary mixture of CO2, methane, nitrogen and hydrogen in the proportion 1-1-1. We note that at any given total fugacity of the bulk gas phase, Ft, the selectivity depends on the mixture composition. To highlight that aspect, I take a binary mixture at a total pressure of 10 to the power 6 Pascal or 1 megapascal, and I plot the adsorption selectivity as a function of the mole fraction of CO2 in the bulk gas phase. We note that the CO2 methane selectivity increases by a factor 2 from 10 to about 20 as the mole fraction of CO2 in the bulk gas mixture increases. To understand this behavior of the selectivity and its dependence on mixture composition, I resort to the ideal adsorption solution theory in the subsequent slides. Watch also my presentation on the IAST explained and the spreading pressure concept on my YouTube channel. The description of the thermodynamics of mixture adsorption begins with the Gibbs adsorption equation, written in this form: A differential of pi equals the sum of the product of the molar loading of component I times the differential of the chemical potential of component I. A is the specific surface area, and pi is the spreading pressure within the units of newtons per meter. At thermodynamic equilibrium, the differential of the chemical potential of component I is related to the differential of the partial fugacity in the bulk of fluid phase by this expression. In the ideal adsorbed solution theory of Myers and Prausnitz, the partial fugacity of component I in the bulk fluid phase is related to the mole fraction of component I in the adsorbed phase by an expression that is the analog of the Raoult's law for vapor-liquid equilibrium. Pi superscript 0 represents the sorption pressure of species I, and the sorption pressures satisfy this expression that implies that the sorption pressures are such that the spreading pressure for mixture adsorption equals the spreading pressure of component 1 on its own and the spreading pressure of component 2. In these integrals, these represent the unary isotherms for component 1 and the unary isotherm for component 2. Since the surface area A is not easily accessible, it is convenient to define the surface potential phi as the spreading pressure times the specific area divided by RT. The surface potential can be determined from information on the unary isotherms. For the special case in which the unary isotherms are described by the Langmuir isotherms with saturation capacities Q1 sat for component 1 and Q2 sat for component 2, the integrals in the previous slide may be determined analytically to obtain phi in the following form. We also have the relation between the mole fraction in the adsorbed phase with the sorption pressures for component 1, the mole fraction of 2 in the adsorbed phase, which is equal to 1 minus x1, is related to the sorption pressure for component 2. Inserting these into the expression for the surface potential, we obtain the following relationship. Now, for a given set of partial fugacities of components 1 and 2 in the bulk fluid phase, and from information on the unary isotherm data fit, we know B1 and Q1 sat, B2 and Q2 sat, we can determine the mole fraction of component 1 in the adsorb phase by solving this nonlinear equation. This cannot be solved analytically except for the special case where Q1 sat equals Q2 sat. In that case, the solution to this expression corresponds precisely with the binary Langmuir model. For the general case where the saturation capacities are unequal, we need to obtain the solution to this nonlinear equation by use of a root finder. And after solving this equation for the mole fraction x1, we can determine the sorption pressures by use of these expressions here. There's a further point to be made regarding the adsorption selectivity. The adsorption selectivity is defined as the ratio of the molar loadings to the ratio of the partial fugacities in the bulk fluid phase. And this expression may be rewritten in terms of the mole fractions, x1 and x2. And in view of this expression relating the partial fugacities and sorption pressures and mole fractions, we write the adsorption selectivity of 1 with respect to 2 as the ratio of the sorption pressure of 2 with respect to the sorption pressure of 1. Now, for the thermodynamic equilibrium to hold, the sorption pressures P10 and P20 yield the same value of the surface potential. And therefore, these expressions imply that the adsorption selectivity is uniquely determined by the surface potential irrespective of the compositions in the bulk fluid phase mixture. We shall test this conclusion using CBMC simulations of mixture adsorption equilibrium. In order to test the conclusion reached in the previous slide, that the adsorption selectivity is uniquely related to the surface potential, we carried out configurational-bias Monte Carlo simulations for a variety of mixtures. The yellow diamonds represent 50-50 CO2 CH4 mixtures. The red circles represent 20-80 CO2 CH4 mixtures. The blue triangles represent mixtures of CO2 and methane in which the total fugacity is held constant at 1 megapascal, and the composition of the mixture is varied from 0 mole fraction CO2 to a mole fraction of unity for CO2. The crosses represent ternary mixtures of CO2, methane, and nitrogen in the proportion 20-40-40. The pluses represent ternary mixtures of CO2, methane, and hydrogen in the proportion 10-20-70. And the cyan-colored hexagons represent data for a quaternary mixture of CO2, CH4, nitrogen, and hydrogen. The y-axis is the adsorption selectivity of CO2 with respect to CH4 in all these mixtures. And we see that the adsorption selectivity is uniquely related to the surface potential phi as plotted on the x-axis. Precisely, this is the dependence that is predicted by the IAST. The dashed lines represent calculations of the IAST theory using data on the unary isotherms. So the adsorption selectivity of CO2 with respect to methane in a variety of mixtures can be predicted on the basis of data on the unary isotherms. The same conclusion regarding the uniqueness of the dependence of the adsorption selectivity on phi holds for CO2 nitrogen mixtures, CO2 hydrogen mixtures, mixtures of methane and nitrogen, mixtures of methane and hydrogen, and all this data is available in this publication. A different way to demonstrate the unique dependence of the adsorption selectivity on the surface potential for binary and ternary mixture adsorption in microporous crystalline materials is to construct a three-dimensional plot of the adsorption selectivity as a function of phi, the surface potential, and the composition of the mixture in the bulk phase. I show here data determined from CBMC simulations indicated by the symbols here. The red symbols, the red circles are for 50-50 mixtures of carbon dioxide and methane in MFI zeolite that consists of a set of intersecting channels. Here the straight channels and zigzag channels. The green squares are the CBMC data for a ternary mixture of carbon dioxide, methane, and nitrogen in the proportion of 5, 15, and 80. And from the data for the ternary mixtures, we determine the adsorption selectivity for the binary pair in that ternary mixture. The yellow diamonds are simulations for the adsorption selectivity of CO2 with respect to methane in a ternary mixture of CO2, methane, and nitrogen in the proportion of 20, 30, and 50. The IAST calculations are shown by the blue-colored three-dimensional mesh. And the IAST anticipates that the selectivity of CO2 with respect to methane for both binary and ternary mixtures is uniquely determined by the surface potential and independent of composition in the bulk gas mixture. The unique dependence of the adsorption selectivity on the surface potential, as witnessed in the foregoing slide, does not hold for mixtures that are subject to molecular clustering due to hydrogen bonding effects. This is the case for water ethanol mixture adsorption in different microporous materials. I show examples of mixture adsorption in chabazite, in DDR, and in ZIF8. And I plot here the adsorption selectivity for 595 mixtures of water and ethanol, shown by the inverted triangles. The blue triangles are the selectivities obtained from configurational-Bias Monte Carlo simulations for 50-50 mixtures. And the open stars are the water ethanol selectivities in water methanol ethanol mixtures in the proportion 1:1:1. So the mole fraction of water in the bulk fluid mixture is 0.05 for the pink inverted triangles. It's 0.333 for the ternary mixture, and it's 0.5 for the blue triangles. We see that the CBMC data show that the water ethanol adsorption selectivity is strongly composition dependent and is not uniquely determined by the surface potential. The IAST predicts that all three mixtures should follow a simple dependence shown by the dashed line. The CBMC data shows strong deviations from the IAST predictions due to strong thermodynamic non-idealities. The same is true for water ethanol mixture adsorption in DDR zeolite and water ethanol mixture adsorption in ZIF8. The theoretical background to the reasons behind the failure of the IAST is discussed in my ACS Omega paper published in 2020. A different way to demonstrate the failure of the ideal adsorbed solution theory in cases where we have molecular clustering is to construct a 3D plot of the adsorption selectivity as a function of the surface potential, phi, and the composition in the bulk fluid phase mixture. Here I show a CBMC simulation data for 4 different types of campaigns. The first campaign is for 50-50 mixtures in which the total fugacity in the bulk fluid phase is varied from low values corresponding to the Henry regime to post-saturation conditions that is attained at a total fugacity of about 1 megapascals. These are represented by the red circles. The green squares are simulations in which the mole fraction in the bulk fluid mixture is 0.05 for water, and the total fugacity is varied from say 1 Pascal to about 10 megapascals. The yellow diamonds are simulations in which the total fugacity in the bulk fluid mixture is maintained constant at 10 kilopascals, and the composition of water in the bulk fluid phase is varied from 0 to unity. And the inverted pink triangles for water ethanol mixtures in which the bulk fugacity is maintained at 1 kilopascal and the composition of the mixture is varied from 0 to 1 for water. The 3D mesh here are the anticipation of the ideal adsorbed solution theory that mandates that the water ethanol adsorption selectivity is uniquely dependent on the surface potential and is independent of the bulk composition. We note that the CBMC data do not lie on the 3D mesh that was created using the IAST, and there are strong deviations from the estimates of the IAST.